Today I do some very simple problems on determinants by following the properties as was discussed earlier. Now we take the first example. Prove that 1a squared 1a squared 1 equal to a cube minus 1 whole square. To do this problem solution, let delta equal to, you write this determinant 1a square 1a square 1. Now you may write or may in symbolic process this equal to 1 plus a square a square plus 1 plus a 1a plus a square plus 1, keeping all others same. What is the operation? C1 dash goes to C2 plus C3. That is, adding the sum of elements of second and third columns to the corresponding elements of first column, and symbolic notation is like this. Now you take common 1 plus a square and 1 a square 1a square 1. Okay. Now write this determinant equal to 1 plus a square, as was discussed in earlier. If all the elements either belongs to row or column are exactly same, then if they belongs to the column, we subtract the elements of first row from corresponding elements of other two rows. So we operate that. That is, we use the property a square 0 0 1 minus a minus a square minus a 1 minus a square. What's our operation? R2 dash goes to R2 minus R1, R3 dash goes to R3 minus R1. Now 1 plus a square. Now you see, if we take a common from this, so it will give you a into 1 minus a. So you can take 1 minus a common from second row. 1 minus a. if you get minus a common from this, then you will get 1 minus a, and it will be 1 plus a into 1 minus a. Then you also take common factor 1 minus a from elements of third row. So this will make you 1 minus a whole square. 1 a square, 0, 1 a, 0 minus a, 1 plus a. Now we expand this determinant by considering the elements of first column. I have already told that one may expand either considering the elements of first row or by considering the elements of first column. Here, since there are 2 zeros in the first column, we expand the determinant by considering the elements of first column to get 1 plus a square. You write this a minus 1 whole square, as because a minus b whole square equal to b minus a whole square. We expand this, so it will be 1 plus a minus a square, so it will make this. So you will ultimately get a minus 1 whole square into 1 plus a square whole square. So a minus 1 a square plus a plus 1 whole square equal to a minus 1 a square plus a plus 1 whole square, and ultimately this will give you a 2 minus 1 whole square. Proof. Okay. Write this first. Now we take my next problem. Prove that a plus b, 2a plus b, 4a plus b, 2a plus b, 3a plus b, 5a plus b. 3a plus b, 4a plus b, 6a plus b equal to 0. So, we know that if the elements of any 2 rows or any 2 columns are identical, then the value of the determinant becomes 0. We now try to make it on that form. We write let delta equal to this equal to. Our interest is to make the elements of any two row or any two column identical. You subtract the elements of first column from corresponding elements of second column and at the same time from corresponding elements of third column. So you keep the elements of first column same, subtract this from this, 2a plus b minus a minus b, 2a plus b minus a minus b. Subtract this element from this element, 3a plus b minus 2a minus b. Subtract this element from this element, 5a plus b minus 4a minus b. Then you subtract these elements from the elements of third column also, 3a plus b minus a minus b, 4a plus b minus 2a minus b, 6a plus b minus 4a minus b. And you write the operation made on the right side of this resulting determinant. C2 dash goes to C2 minus C1, C3 dash goes to C3 minus C1 to get first column dimension a plus b, 2a plus b, 4a plus b. This is a, this is also a, this is also a. This is 2a. This is 2a. This is 2a. Okay. So this is our resulting determinant. Now our property was that if some element or column, if some elements in a column we obtain in common form, that is the second column contains all elements A and that is common, so that can be taken outside of the determinant sign, as well as 2A is the common elements of third column, so that can also be taken outside of the determinant sign. So you write this equal to A from here to A from here, so it will give you twice a square. It remains same, a plus b, 2a plus b, 4a plus b. It becomes 1, 1, 1. It also becomes 1, 1, 1. We see that the elements of second and third columns are identical. Therefore, the value of this determinant by that property becomes 0, and it will give you equal to a square multiplied by 0 equal to 0, since the elements of second and third columns are identical. Okay? This is very simple problem. We consider some simple problems to solve them first, and readily we will go through our harder problems. Now we take our third problem. What will be the third problem? My third problem is that prove that determinant A, B, C, A square, B square, C square, BC, CA, AB equal to another determinant 1, 1, 1, A square, B square, C square, A cube, B cube, C cube. So that means we reduce this determinant to that form. Write the problem first. Leave it. Solution. Let delta equal to. Here, this is BC, this is CA, and this is AB. We multiply each term of first column by A. You see the property, if delta equal to K1, A2, A3, KB1, B2, B3, KC1, C2, C3 equal to, what was my result? That can be taken outside because it is a common factor to all the elements of first column. A1, A2, A3, B1, B2, B3, C1, C2, C3, where K is a non-zero constant. Now, suppose the original determinant was this, K into this. Then one may write this determinant equal to this. Now, we take this determinant in the form we write ABC by ABC. Anyone may write this because this is 1. A square, BC, B square CA, C square AB. Now we always proceed to make it easy as we need, and here we have two options, A, B, C. By ABC we may take, say, A from here. A from here, suppose A was a common factor to all the elements of any row or column. B was some common factor to all the elements of any row or column. C was some common factor to all the elements of any row or column. Here we introduce A as a common factor to all the elements of first column, that is, we may write here 1, keep ABC here, and we introduce A as a common factor to all the elements of first column to make them A square, A cube, ABC. B to the elements of second column. C elements of third column, and therefore ABC is not here, but this has no role to this determinant, so it keeps outside the determinant sign. Now you see all the elements of third row are ABC, so that can be taken outside of the determinant sign as a common factor. So you write this. A square, B square, C square, A cube, B cube, C cube, 1, 1, 1. Okay? Very interesting. So this is as a common factor out. Now we see our determinant on the right side. We see that there was 1, 1, 1 in its first row. So we now interchange the elements of first and third rows. 1, 1, 1, A cube, B cube, C cube, A square, B square, C square. Since we have interchanging the elements of first and third rows, so our property was that one minus sign will be a common factor of that determinant. The statement was that if we interchange the elements of any two rows or columns, then the value of the determinant remains the same with opposite sign. That was plus, and it will opposite sign, it will give you minus. Now again you interchange the elements of second and third rows. 1, 1, 1, A square, B square, c square a cube b cube c cube. So you will get another minus. There is a minus, so it will make you plus. That was our problem, and we have already used our property which was learned earlier, and this determinant converts to another determinant by using all those properties. Write this first. We now take another problem. All the problems you see are very interesting. They are very easy also. Readily we see some harder problems. Before that, we discuss about different types of problems, more properties of determinants, and then proceed. Now, you take another example. PT, prove that 1 plus a square minus b square twice ab minus 2b twice ab 1 minus a square plus b square twice a twice b minus twice a 1 minus a square minus b square equal to 1 plus a square plus b square whole cube. To do this, we use another property. Solution. The property was that if we add or subtract some multiple of the elements of any other row or column to or from the corresponding elements of any other row or column, the determinant remains same in its value. Here we at first we subtract, because it is minus b square, we subtract b times the elements of third column from corresponding elements of first. To write 1 plus a square minus b square, subtract, so this is minus minus plus b times twice ab minus twice ab twice b minus b times 1 minus a square minus b square. At the same time, we add a times the elements to the corresponding elements of second column. Twice ab add a times 1 minus a square plus b square plus twice a square, add, so a times minus a cube minus ab square, and that remains same, twice b twice a 1 minus a square minus b square. Now you write the operation on its right side. C1 dash goes to C1 minus BC3. C2 dash goes to C2 plus A C3. A C3. C1 dash goes to C1 minus BC3. C2 dash goes to C2 plus A C3. What is the result? Equal to one plus a square, and it will be then after this line. This is after this line. 1 plus a square plus b square. This becomes 0. 1 minus a square plus 2a square, that means 1 plus a square, and 1 plus b square remains the same. 2ab minus 2ab, that becomes also 0. 2b minus b, that means b plus a square b plus b cube. So it will be b plus a square b plus b cube. This is the result after this. And this is minus a minus a cube minus a b square, and third column remains same. You see 1 plus a square plus b square 0. If you take b common, then 1 plus a square plus b square. So you can take 1 plus a square plus b square as a common factor from first column. So it will 1, 0, and this is b. Here also you see this is 0. 1 plus a square plus b square, you take minus a common, then you will get minus a into 1 plus a square plus b square. So it will 1 and it will give you minus a. So here is also another common factor, and it will make it whole square. This remains same. One minus a square minus b square. Okay. Now you can expand it. Whole square. Put a third bracket. 1 into this minus this. 1 means 1 minus a square minus b square, and this is minus minus a plus 2 a square. Okay. This is 0, so that will be 0. Minus 2b into 0 minus b. minus b. Complete the bracket. This will equal to 1 plus a square plus b square whole square. What's the result in this bracket? 1. This will give you plus a square minus b square, and this is plus 2b square. Then 1 plus a square plus b square whole square. You will get another 1 plus a square plus b square, and ultimately you get one plus a square plus b square whole cube. Proved. Okay, clear? Write it. Now we take another example. Without expanding, so that suppose one column, the column 1 contains these elements: omega, what is omega? We have already learned, as I hope, the complex number, and in the complex number you see omega cube equal to 1 and 1 plus omega square equal to 0. That was in the complex number. When I teach you about complex number, I will explain everything in details. Now, this is our determinant. We have to, without expanding, so that this is equal to 0. To do this, let delta equal to 1 omega square, 1 omega square omega square 1 omega. Okay? Now we adding the sum of the elements of second and third columns to the corresponding elements of first column equal to, you get one element, first element of first column. Adding the sum of these two elements belonging to column 2 and column 3, sum is 1 plus omega square, and that sum we add to the corresponding elements of first column. Sum omega square plus omega, so omega square plus omega, omega square plus omega plus 1, and these are the elements which keeps unchanged 1. Our operation, you write it on the right side of the determinant always. C1 dash goes to C1 plus C2 plus C3. In short, that is in symbolic form. So you get this is 0, this is 0, this is 0. So equal to 0, 0, 0, 1, omega square, omega, omega square, 1. Clearly this is 0. All these elements are 0. Why clearly 0? If you expand by considering the elements of first column, you get 0 into something 0, minus 0 into something 0, plus 0 into something 0. So the result will be 0. So we have proved this problem without expanding. So this is my today's class, very short class. Next occasion I will discuss more problems that may be hard, may be simple, and more other properties about determinant. You follow my videos. If you feel that it helps you, put a like and make comments in my comment box, and to help your other friends, always share this video. Thank you all of you.